All right, welcome everybody. Today we're going to go over a design exploration of our 2024 robot Ultraviolet. We're also going to talk about the game a little bit, um, so we understand why we built it the way we did in the context of the game. Okay, so every season we get a brand new game given to us. First Saturday in January. This year it's going to be like the 4th, I believe. And so we find out what the game is, and then we have to fully decide how to play the game and everything. And that's a lot of what we're going to talk about and how we actually go through the design is how do we actually play the game. So we can look at, oh, that did not work. There it was. Okay, that's a little bit better. Whoa, that was loud. Let's not do that. Let's make it a little quieter. Oh, and then it went and did all sorts of weird. Why is it being weird? That's good enough.
Welcome to the 2024 First Robotics Competition game, Crescendo, presented by Haas. 2 alliances of 3 teams each compete to score or play notes in 3 different field elements, amplify their speaker, get on stage, harmonize, and take the spotlight before time runs out. Alliances earn additional rewards for meeting specific scoring thresholds and for cooperating with their opponents. Robots start each match inside their alliance's starting zone and may be preloaded with a note. During the first 15 seconds of the match, robots are autonomous and can be programmed to leave their starting zone, play preloaded notes in their speaker or amp, and collect and play additional notes. During the following 2 minutes and 15 seconds, drivers control their robots. Robots collect notes from human players at their source and play them in their amp and speaker. Each time an alliance plays 2 notes in their amp, the human player can hit a button to amplify their speaker for 10 seconds. Notes played in an amplified speaker are worth more points than those scored in an unamplified speaker.
A human player may choose to play a note scored in their amp to cooperate with their opponent. If each alliance plays a note by hitting their cooperation button in the first 45 seconds of teleop, all teams in the match receive a cooperation point, which will influence a team's rank in the tournament. The number of played notes needed for a bonus ranking point is also reduced.
Robots are protected from contact by their opponents when at their podium, off the ground, and during the last 20 seconds of the match while in contact with their stage. As time runs out, robots race to get on stage and deliver notes through the flap and into the trap. Bonus points are awarded for harmony when robots on stage use the same chain. On-stage robots earn even more points if a human player spotlights the robots on a chain by scoring a note on the chain's corresponding microphone. The alliance that earns the most points wins the match.
All right. So looking at that as basically how we're given the challenge every year is we have some sort of animation, then we're also given the full manual, which goes through all the exact rules. So the animation kind of gives us a summary, gives us kind of an idea of how we're going to have to play the game and what kind of tasks we have to do. But then our job is to read through the entire manual and kind of start figuring out how do we actually think robot play is going to work, and how do we start breaking down the actual tasks that the robot are going to have to do for us to be able to design a quality robot that's going to do well at the actual events. So even though that was like that 2-minute video and it talks about all of the different things the robot can do, we end up breaking it down to a relatively small subset of things, what we actually care about doing. And so the simplest form of this game is the robot has to be able to pick up notes. They don't actually have to, right? You could have them always get them from the human player and get them dropped in. But we just know that was going to be slower, right? If you ever miss a note, you don't want to have to drive all the way down to the other end of the field, get a new one. You'd rather just be able to pick it up and score it again. We need to be able to launch notes into the speaker. That's where you get a lot of the points are from putting them in the speaker directly. And then the amp was there to be able to make your score even higher if you could coordinate basically the pattern at which you were scoring. And so we wanted to be able to amp really fast too. And then for the end game, the way it all ended up playing out with points is it made the most sense to be able to, if you could do it quickly at least, to climb and put a note in the trap. So that was if you were going to do everything in the game, you basically had to do those 4 things very well. And that's kind of how we went through and started figuring out, okay, how do we actually now build something that meets all of the rules? So there's a weight limit, there's a size limit, there's different parts of the game that we're thinking about how you have to play them. So you have to be able to like drive under the stage. So that puts some requirements of what the robot looks like and what it's able to do as well. So a lot of those things go into the final product that we end up getting to. So a lot of this is through testing. We'll build as much of the field as we can. So we have a wooden version of the stage. We have wooden versions of the goals. So all of those things that we can early on be prototyping and testing different mechanisms and different concepts to then figure out how they actually integrate into a final robot. So the basic concepts of almost all of the robots that we're going to build is that we're going to divide them up into mechanisms. Some teams call them subsystems. Those 2 terms kind of get intermingled. And roughly they're all going to be kind of able to be assigned into some combination of these 4 things. So every robot's going to have a drivetrain. That one's kind of special and specific. It's the thing that moves us all around, that moves the robot around the ground. Almost always going to be on carpet. Sometimes the robots have to drive on platforms and things. Sometimes it's plastic. Most of the time we're worried about the actual carpet interactions and how we can get more traction and how we can efficiently move around without taking up too much of our battery. Allow our driver or pilot to control the robot really well, make sure it's doing what we expect, make sure it's going to work really well in the autonomous mode at the beginning of the match. So all of those things kind of go in to fitting into how our drivetrain works. The other big thing with the drivetrain is it has to be super reliable. So we don't want to take a ton of risk with our drivetrain because if anything happens to it and we can't make it reliable in matches, that's the easiest way to have a bad robot is if your drivetrain isn't working every single match. The other 3 are how we make the mechanisms that actually interact with the game pieces and things. So the most common one that we have on basically every single robot we've ever built will have some type of roller almost every time. There's probably some games where you wouldn't have a spinning roller of some type, but almost every one does. And this is basically just spinning some sort of wheel or spinning a long tube or roller. And we control that in software, so we can set its velocity, or in theory, exact position too, if we needed to tell it to roll so many number of rotations if we wanted to. But this is normally things like our intake, so the thing that's going to suck up the note in this game and bring it into the robot, or anything that's moving the note around the robot. Those are all just powered by different rollers, and we're able to spin them and direct them into different places. And then we also have arm mechanisms, or anything where we're going to set the angle that we want it to go to. So in different games, we may have to like reach up really high, and an arm may be the right option to do that. In this game, we had to be able to like set our launch angle for the launcher that actually throws the note out, and so we had a pivot that we were able to set the angle to that had a bunch of rollers on it to actually do the launching. And then we also have linear mechanisms, which are anything that we want to set a certain position to along like a line, basically. So any of our elevators or slides that we might have, our climber this past season, which we'll look at in a second, all of those are linear mechanisms. And so kind of how we were able to build all of these things and combine them is largely what we do to be able to make our different robots. And we make different combinations of them, and there's different ways to build each one of them. And so a lot of the point of the design explanations that we're doing now is to show a lot of the different ways we can combine these mechanisms and different ways we can implement them to find the right option for each design challenge, design task that we have. So most of what we're going to spend today on is looking at our 2024 robot. Ultraviolet, we have it hopefully loaded. There it goes. All of the robot CAD for our team is done inside of Onshape. It's a browser-based CAD program that lets us fully design every part of it, every hole on the robot is fully done in CAD before we ever produce anything. There's some stuff that we won't CAD exactly, so a lot of like the actual wiring and things we won't put into CAD, but we will think about where it all goes. Um, so we do know if we put a motor somewhere that has to have wires running to it, we do have to think about how the wires are going to get to that motor. Um, and so we will leave space sometimes, or we will sometimes CAD different parts of it to make sure we have a good concept of where the wiring is going to go. But nearly everything else, pretty much every mechanical feature of the robot, any piece of plastic, anything like that, will get put into CAD. Okay, so looking through this, we end up having 5 subsystems. That's roughly what we try to break robots into. Sometimes we have to get up to 6. Sometimes there might be a fewer ones if the robot ends up having some things that are more integrated. But there's roughly 5. And so the 5 that are on this robot are the drivetrain, the intake, the launcher, the amp trap mechanism that's able to put the notes in the amp and then also extend higher and put them into the trap when we climb, and then the climber itself. Uh, the CAD here will have some hidden parts and things, but this is largely pretty much exactly what our competition robot looks like right now. There's a few tweaks that are on the robot that aren't shown in CAD right now. There are different versions of parts and things, but the vast majority of things are correct, or at least in some version of our robot. So our about state champs version, this is very much close to what it was looking like. All right, so we're gonna look at our drivetrain here. So we can open link document and that'll pull us over to just our drivetrain document. And so the drivetrain is relatively simple in this robot. There's not a whole lot going on. Some of the basics here, we have our frame, so the tubes that go along the outside of the robot are going to be the frame for the robot, and this kind of gives us our base structure to mount everything off of. And then we have our belly pan. And so this connects the main 4 sides of the robot and gives us kind of this middle structure to be able to mount a lot of our electronics. It also holds some amount of the actual robot structure together too. So a lot of these holes are for mounting the amp trap elevator and parts of the launcher mounting as well. The absolute base for the robot, then the way it actually drives, and pretty much for near 80+% of robots now or something along those lines, it's getting higher and higher each year, are our swerve modules. And so in the corner of every competition robot we'll probably build for the foreseeable future, we'll have swerve modules in the 4 corners, unless it's an incredibly strange game for some reason that drives us in some other direction. This kind of standard packaging has become the default. It's pretty much looked the same way since our 2022 robot. They've had pretty similar drivetrains. The swerve modules work in that you have one motor on each module. So in this one, this motor here is powering the steering of the wheel. So the wheel's able to fully spin 360 degrees and can point in any direction. And then the other motor is powering the actual driving of the wheel, its velocity, which isn't set up in CAD, but you would imagine it like it's driving around, moving the robot. So if all the wheels are pointing in the same direction, that's the direction the robot can go. But then our software can do all of the math that allows us to have the robot be spinning while driving in any of the straight lines. We can drive sideways at any angle. We can spin in any direction. We can turn the wheels all into like a X configuration, so then the robot can't be pushed very easily. And so all of that's happening without the drivers having to like manually turn each wheel or anything. All of that math is being done by the software running on the robot. So if you point the stick, the one that's controlling the robot forward, the robot just goes away from you, no matter which way it's pointing. So you can spin it while pointing away from you. It's still going to drive away from you while turning. So it's a very intuitive way to control the robot, and it gives us a lot of flexibility compared to a robot that just has what we'd call like standard tank drive or differential drive, where you have the wheels, we have 2 rows of wheels on each side, and you're only able to turn kind of like a construction equipment, like a skid steer, um, bulldozer, or something would be able to drive. And that worked for a long time. All of our robots pre 2021 were driven that way, and it did work. But now Swerve has just gotten a lot easier. A lot of the things needed to be able to build these drivetrains have gotten either cheaper or more performative to where they perform better. A lot of the other rules around them were relaxed to make it easier for teams to do. And so more and more teams, and pretty much every team, one of their first goals now is to figure out how to get to a productive swerve drive. As you can just do so many more things, and it makes all your other mechanisms easier to build once you're able to drive sideways. And you don't lose any traction or anything either. Um, some of the small things we do, so we also have the bumper mounts going around the whole outside. So you have the bumpers here. We can go ahead and hide some of that part. This is the wood on the inside that we needed, so we knew where like the holes were. So we're making the templates for that. So that's why those are catted separately. And then this one did have some um, special features compared to most years, where we had this upper frame mounted at a different place than the lower frame, so that our intake could basically be beyond our wheels. This gave us a really wide intake. We'll look at that in just a second. But it did mean our frame had to be a little bit different here. Similarly, we had to have a smaller tube down here so that the note could go over it instead of the 2-inch tall tubes that we have on the sides normally. There's some other just integrated features into the robot, things like handles, so that we can pick the robot up easily. Those are things that not every team does, but it does make just life easier, just the quality of life of having to maneuver the robot, work on it, having the handles to pick it up and off the cart and things and set it on the field is a lot easier than just trying to grab it by its frame every time. We also have sponsor panels. These are just polycarb plates that we laser cut, and then we can have printed out um, posters basically that we can tape to the back or laminate and tape to the back, which let us recognize all our sponsors and make the robot look a little bit better. And the last part of the drivetrain is basically our battery box, which was just a couple pieces. Started off as polycarb, and then they did crack over time. The robot just takes a lot of impacts, so we ended up switching them to aluminum. But relatively simple. There's some standoffs that connect up into here as well, and then a strap that holds the battery into the robot. There are a few other like guards and things to stop the notes from falling into the robot and staying there. You were only allowed to hold one note at a time in this game. And so you didn't want a note getting stuck, so we did a lot of work to make sure the notes couldn't get stuck in the robot. I think that's most of it. This upper frame rail section, so not every team does this either. This is something we borrowed from a team up in Michigan, the Robo Jackets. They had done it on their 2023 robot, and I think a couple of robots before this. And this just gives us a nice mounting place for various mechanisms and things that we're able to attach to when we need to, and you don't have to always be trying to mount to this lower frame, which sometimes gets hard where the swerve modules and things. You can also mount more stuff into the corners. It is a bit of a weight hit because you do take the weight of having it, but it does back the bumpers a little bit better, and it just gives you a lot of places and options for mounting quickly when you don't necessarily know everything that's going to be designed into it ahead of time. Having this here is pretty useful, and so we did this on our 2023 off-season robot that we built, and then carried it over into 2024. And if it fits again, if there's some reason not, or if there's some reason, if it's reasonable to do it again, what will likely happen on our 2025 as well. We liked it pretty well in 2024. We also designed it into the Catathon robot that we were just designing, and so having something like this does seem to work pretty well. From there, we go on to the next mechanism, which this year was the intake. I think we can just do it in here. So you can kind of isolate and see how this works. So everything that's not part of the intake gets hidden. So that gap that we were talking about behind this frame rail is where we're able to stick the intake. This was something we definitely had to prototype quite a bit. We weren't sure exactly how much room we were going to need. Um, we ended up being able to do it in a pretty small amount of space. I don't think it lets you. Here we can look a little bit. So this whole thing was able to only be in about what, 3.5 inches. And so this was very much a unknown when we first started. We didn't know how much room we needed to leave beyond the swerve module and behind our normal frame. Um, and this would have impacted quite a few things. So this robot's basically at the max dimensions you can be, or pretty close. It's about 29.5 by 29.5. And so if we needed to add, if we needed the intake to be like a 1/2 inch wider, that would have needed us to move our swerve modules a 1/2 inch forward. They don't really have that right here, so that means our whole elevator would have had to move forward too. So a lot more of the design would have had to change if we needed more room for the intake. So this is one of those things that we had to figure out pretty early if we were going to be satisfied with how much room we left. Was it going to work the way we wanted it to? And so we built a wooden prototype pretty quickly. We're able to power the rollers and kind of see if we could get it to intake the node as nice as we wanted to. These are relatively standard way that we had been building various rollers over the years. These are polycarbonate tubes on the inside here. So this is just a clear plastic tube on the inside. We stretch silicone rubber over the top of it. So we buy like silicone rubber tubes that normally have a little bit smaller um, diameter than the actual plastic one, and we stretch it over it so it gets a good fit and won't like roll too much, or it won't slide or anything if it was too big. And then we're able to print these pulleys on the outside that we use our 3D printers for. And we're able to make this part that we then glue in and then drill and bolt as well these hubs into the ends of the rollers. So these little gaps are filled with hot glue. Some special industrial hot glue is what we were using, but you could use other things. We wanted them to be able to be removed. We didn't want to use something that was permanent like epoxy, because we did want to be able to swap them out and still keep the roller, because the roller does take some amount of time to make. And then these also hold the bearings on the inside. So there's a bearing here, and there's a small shaft running through. Let me hide the spacer. And then we have this shaft here that's running all the way across. And so this shaft doesn't spin. So this is what we call a dead axle. So we bolt this shaft directly to the plate. And this shaft acts a little bit like a frame member or support for this plate to give this whole thing structure. So it's acting as a standoff going all the way from one side to the other. So you can't squeeze these plates together. So if you do get hit here, or you start trying to bend this, this standoff and the lower one that are made the exact same way prevent that from happening. So it allows your rollers to also act as structure for the whole robot. And so we use this concept quite a bit, where we have this dead axle running through. And so we're not having to spin the axle, we're just having to spin the roller on top of it. The bearings here are similar to like bearings you'd find in a skateboard or anything like that, or a fidget toy, like one of the fidget spinners. They have little balls inside of them that give it very low friction, so we're able to spin these quite fast without them heating up or anything, or without them wasting a lot of energy. So anytime we have something that's spinning really fast, we want to make sure we're using ball bearings so that we can reduce that friction as much as possible. The 3D printed pulleys here are powered by this belt. So in CAD, we just have it CADed as like a simple rectangle, but in real life, these have the same sort of belt teeth that, or would be the opposite of here, so it can engage and power this and spin it. Inside this gearbox, we have a couple overlapping gears, because originally we were 3D printing this setup, so we had these 3D printed gears. We've stopped doing that. We were able to slip a couple of them early on, so we ended up switching out the way this was powered, and we made a pretty compact way to have a belt and gear here to be able to actually reverse these rollers. So the concept here is that this roller from this direction is spinning counterclockwise, so it's coming around like this. And the roller up on top is spinning clockwise, so it's going in like that, so that once the note touches here, it kind of gets lifted up, touches this one, and then gets sucked into the robot. So because we need to have these spinning in opposite directions, we can't just power both of them from a belt from the same motor, or they would always be spinning in the same direction. Let me hide the little wedge here. And so these two gears up here are what give us that reversing effect. And so anytime one of the simpler ways to reverse motion is just to have two gears. Since they're meshed together, they'll always be reversing each other's direction. So this one at the top is going to spin the same direction as this roller, since it's belted directly from the motor shaft. And then since this one is now reversing, we can have another pulley here that powers this lower shaft. So we can have a very compact gearing solution. It doesn't take up very much space at all. We knew we didn't want it to take up too much room, right? It could have come back a little bit, but it couldn't really go that much further out, or it was going to start hitting the swerve module, or it was going to start hitting the frame here. So we had to package it in a pretty small space to actually allow it to do what we needed it to for us to be able to intake. A couple simple things we also do. We knew we didn't really want our intake to be intaking all the way over here on the corner. It's pretty bad sometimes if you can get some jams in there. It's harder to get. Same with like over here, you don't want it to like go up into these belts at all. And so we put the little wedges there to kind of stop the note from catching too early. That also allowed us just to leave these pulleys over on this side of the roller. These aren't used on the robot directly, but it does allow us to have spare parts basically built in. So if something were to happen to the teeth on this pulley, all we have to do to be ready for the next match is unbolt here and from the other side and flip the roller around because it's symmetrical, and we can start using this brand new untouched pulley immediately without even having to do any repair work, without having to have a spare somewhere else. We have the spare basically built in to the robot. This also allows us to make everything symmetrical. We don't have to worry about different pulleys being different. There was also some ability, since this whole setup is symmetrical, if we really wanted to, we could have had a mirrored version of this gearbox and motor over on the other side. And at some point in the middle of the season, we could have decided, oh, we want two motors powering our intake, and we could have done that. It allows every part to be the same. From both sides, we just have to mirror them when we like print. So like these wedges here, they just get printed mirrored, so we don't even have to do much of, we don't have to do a whole different design. Keeping things symmetrical allows it to be a lot simpler and gives us some flexibility throughout throughout the year. If anything were to happen, we can change the robot a little bit and make that work. So let's talk about where are the other parts of the intake we can talk about. So these outside plates were done on our laser cutter. So they were originally just plastic. They were polycarbonate that we laser cut. They attached down to the frame members and up to this upper frame to give it some more support. But we did have some issues with them cracking in certain places. And we were worried about potentially we'd have some of these bolt holes crack and the rollers wouldn't be correct, and we might lose the intake during a match, and we really didn't want that. So we started adding, we were able to get the room to add a little bit of shim plate. So we had some metal plate that we would add to the inside and outside that just secured it so that you wouldn't ever, even if the polycarb on the inside cracked a little bit, you'd always have security around where the bolt holes are. And the plate would be a little bit stronger, so it could always keep running no matter what. So there were a few times where we had to replace things, but once we kind of did do the shielding, this worked pretty well all season. In addition, we have these wedges here. And so they're, this was a little bit of somewhat unintuitive of how we wanted to be able to funnel the note into the center opening. There's really only room for the note, how big it is. It's about it's like 13 inches wide, I believe. There's really only room for it once you account for these motors on the side here for the module. It really goes in without much room on either side. And so part of that was, how do we make sure that if we do get like the front of the note intaked into here, how do we make sure it can wrap around and get centered the way we want it to? And a lot of teams solved this in a variety of ways. Some teams had like powered wheels that were spinning here at a plane, kind of shoving the note over. Yeah, there were several different options for how to do it. We wanted to make sure we could do it ideally passively. It had just less components if we don't have to have anything spinning here. Um, and so we were able to test a couple different things, and this one ended up being a pretty early prototype that we've left all season because it largely did what we want. But for the most part, what it does is the note can come in, can get hit here, and it sort of gets pinched, but it doesn't let it keep going up at all. And so as it does that, the note almost gets like flattened out, and more of the note gets sucked into parts of the roller. And then once the part that gets sucked in over here, it's able to get pushed through more, and the whole thing sort of just like rotates around and gets sucked through more of this main opening because it can't keep going through over here. So it already has it, and it has it in its possession here, but it can't actually get jammed because there's no place for it to go. So this wall sort of just stops the note from getting jammed or pinched too much, but still pinched enough to where it actually does grab it. And then it sort of just waits very, very small amount of time because the rollers are spinning so fast for the rest of the note to spin in kind of around this curved part and up into our robot. There's a ramp here that it then gets shoved up and gets caught by our indexer that gets ready to either feed it into the launcher or feed it up into the amp trap. All right, so from the intake, we can start looking at our launcher. So if we isolate that here, this was a little bit of interesting in that we didn't have a lot of good places to secure it. We didn't have rails running the whole length of the robot, kind of because we had the elevator in the middle and some other things. It didn't make sense to have a full rail. So we were able to just put these blocks of 1x1 down here attached directly to the belly pan. And then we did have a few places where we could attach the launcher out with standoffs out to the frame to stop it from wiggling side to side too much. And that did seem to work. So we were kind of packaging this whole thing inside of these elevator rails that you can see. So nothing could touch out there. Nothing could be mounted because all this part's going to go up and down, which we'll see in just a little bit. This is, again, mostly almost all of this white parts are all done on the laser cutter. So we're able to design all these shapes, exactly where these holes are, and then cut them out. And so we had a couple different iterations of this to get to where we wanted. We were able to use these mounting plates as our gearbox here. So we designed in from our motor down here. We have some more gear reductions. So the motors are spinning very, very fast, and we use our gear reductions to slow them down while still using all of their energy. So instead of just giving them less voltage or telling them to spin slower, they're not able to actually use all of the power that they have if you tell them to do that. So we use gearing to be able to use all of the power they have while doing that at a slower speed, because we don't want this to rotate very fast. We need this to move a pretty small amount. It goes from about 0 degrees, it can shoot about flat, up to 70 or so degrees. And so that's all this whole thing is tilting up and down. And so we need that gear reduction to be able to use the majority of the motor's energy when needed, but at a much slower speed. So we gear down most of our applications unless we need it to spin really, really fast for some reason. So that's what this gear train is here. It comes up into these larger gears. So we have a couple different sized gear teeth. You can see these gear teeth are really large. These ones are a little slower or a little bit smaller. This is called the pitch of the gears. So if you have smaller teeth, you have a bigger number pitch. So this is a 20 dp gear. It's like the standard size. And then this small or these bigger teeth ones are a 10 dp gear. And so we wanted to use these bigger teeth so that they're not going to bend or crack as much, because we had to make our own into this plate. And so this plate here sort of acts like a really big gear, but only a section of it. And so as this one turns, this one moves up and down on top of it. And that's how we're able to set the angle of our launcher. Let me see if I can grab the other face, make it look a little better. There we go. So as the motor turns, it eventually spins this gear. There's one on the other side as well. And this whole thing sort of acts like a rack and can tilt the whole launcher up, and we can set exactly the angle we want to fire the note out at. It shares the same shaft over here to power a second gear. Oh, I got a little bit wild, sorry. So we have another gear here that's doing the same thing. And then these gears are just 3D printed because they don't have any load going on them. They're here to give us another sensor that can tell us the exact angle of our launcher. And this worked out pretty well. These are geared down so that for the motion of our launcher, this spins slightly under one rotation so that we can use the entire range of this encoder. This encoder can basically tell us where it is exactly in a single rotation. So it reads back in our software like 0 to 0.96 or so. And so that gives us really fine control of where exactly we're pointing the launcher at. The launcher has two other motors on it. One we call the indexer. This is what takes the note from the intake and stores it and gets it ready to feed it into the launcher when we're ready to fire. So that motor's down here, and it has a belt that runs up and powers this roller. These are very similar to the intake rollers. They're basically made exactly the same way. Whenever possible on our robots, if we can standardize a part or standardize a way to do something and use that same system over and over again, that makes the season go a lot easier. If everyone learns how to make this roller, then they can just make it at different lengths to the intake, to the indexer, to the amp trap. They're all basically the same. They just have slightly different length tubes for whatever their application is. And so we can just batch print a ton of these. We probably printed, I don't know, 50, 60 of these easily this season, if not more. And so that's able to get powered by a second belt. So both of these rollers spin together. And they're able to hold the note before we actually feed it into the launcher. We do have a sensor that lets us know when the note is there. So the sensor itself isn't in CAD, I don't think, but this is the mounting block for it. And so this lets us see as the note comes up, we can see where it is along this path and kind of stage it in the same place every time before we feed in the launcher, because we really want consistent results coming out of the launcher so that every time the note goes exactly where we want it to. That's the goal, at least. The launcher itself has two motors on it. There's a motor on the left and right side. And what we ended up doing, which isn't quite shown here exactly, we ended up changing a couple things. But originally we had both motors powering the top and bottom of our roller assemblies here. And we ended up changing that, and also a couple other things changed that aren't shown here. These wheels don't exist in real life. There we go. Okay. So what we ended up doing was having one of these motors directly power the lower side, and then this motor directly powered the top side, and they weren't connected between them. So we had one motor powering the top and one motor powering the bottom. And that was to give us, to make the whole system more efficient. The motors would draw less power when they weren't attached to each other versus when they were. And we also changed some of the exact beltings and things and stuff as well to tweak all of that. This launcher looks a little bit different because it does, when you see it on the real robot, it has 6 wheels on one side and then it only has 2 wheels on the other. And the concept there was that basically this first row of wheels imparts a good amount of actual velocity on the note. So this is accelerating it, getting it moving faster. And then these two extra wheels on just the left side provide the note with a lot of spin, because we found that it makes it a lot more stable when you do have the note spinning. And so these two help give it a lot more spin when it comes out. There's a few things as well that we did. So like the walls in here on the launcher are coated with Teflon, so that we can reduce that friction really down a lot. Teflon, the same stuff. It's on like non-stick pans and things, also known as PTFE. And so those have the walls of those are all slick, so that the note when it's rubbing against them isn't gaining too much friction. We did have this a little bit smaller than an actual note, I believe. Yeah, so we look at that, it was like 13.5 inches, so the note compresses a little bit to come through, because the note's like 14 inches wide, something like that. And so it does actually rub the walls a little bit as it's coming through here, but that keeps it perfectly centered. And so we know where it is when it's exiting. It doesn't have the ability to like be too far left or too far right. I think that's most of the launcher. Again, we do use the gears to do the reversing here. We didn't actually need it once we ended up changing it to where we had one motor powering the top. We could have had them spinning in opposite directions directly, but we did end up leaving one of the reversing gears just because of the way the layout was. We didn't want to change all of the belt lengths everywhere. These gears up here are all going to be printed. These versions that we've shown a little bit, but not a ton. So any of the metal gears we had, like on the pivot, those had straight teeth. These gears that have this angle in them, these are called a herringbone gear, or sometimes a double helix gear. And for the most part, they're more efficient. They give you more kind of gear contact when they're touching each other. They're just incredibly expensive to produce if you're trying to make them out of metal. And so if we're not using metal gears anywhere and we're just printing them, we will almost always print 10 dp herringbone gears, as they're just stronger out of plastic and printing, and it costs us nothing extra to print them. And then if we needed them ever to be metal, we would swap them both to regular straight spur gears that are 20 dp, and all the gear spacing would still line up. You just double the number of teeth, going from 10 to 20. Let's see. I think that's most everything. We had a couple little things that we were doing early on. We had like springs assisting the launcher. We ended up stopping that. So these like torsion springs that you'd find in like a mouse trap or something were there to help hold off some of the weight. But we ended up realizing we didn't need it. The motor was more than strong enough to hold the launcher wherever we needed as we geared it down. So we ended up removing the springs from that setup. All right, so that's one of the ways we could score the note. The other two ways we need to score the note are relied on by our amp trap mechanism. So this had quite a lot going on. So this was an elevator along with a roller system. And so the elevator was able to take the note, raise it up, and then deposit it into the amp, or if we had already climbed, deposit it into the trap. Coming back down, the way that transfer actually works is it relies on these two rollers. And so this lower roller here is powered by the amp trap. And so that has, very similar to how the intake is done, this has a motor here, has a gear reduction, because we needed to spin it down. We need to make it go a little bit slower and have that more usable power at the speeds we needed, so we get more torque by having this gear reduction. And then it's belted out to this first roller. And then over on this side, we have a belt going up to the third roller and a belt going down to the first one. So all of these are able to spin together. In addition, we have a couple of the top like hood rollers up here that are also able to spin, but these get reversed on the actual mechanism. Nope, that's not what I wanted. Seem to have lost the. Okay, there's a few things in Amp Trap that are missing, but we can talk about those in a second. Okay, so these two are powered on different motors, so that when we have the indexer basically reversing if it's trying to send the note back down towards the intake, and if this roller is spinning up, so it's spinning from this side view, this is spinning counterclockwise, and this is spinning clockwise, they're able to drive the note up through this gap and feed it on top of this back panel right here into the next rollers to get it to kind of sit up in this area where it's stored, ready to be taken up to the amp or the trap. There was a lot of different testing and iterating that went into this. We had to make sure that we could get this gap correct and that it would actually work to feed up. There are a few times where if the roller isn't clean or if something gets a little bit off that the note doesn't always want to transfer. So we had to play with that quite a bit this season to make sure it was going to do that every time in the match. And then we also just play with quite a bit of work to make sure that the amp scoring and trap scoring could work at the same time. So it was relatively easy to do one or the other. It wasn't very easy to do them both with the same configuration of rollers up here. And so what we ended up finding is we had we did have these gears. This is a different version. We need to fix this in CAD. This is one of the ones that we ended up not using. The competition one, this is a little bit lower, and a few different tweaks went into it. But we did have these two rollers up here that help actually drive it out and down, so the notes kind of come in this way. And then we had what we called our cape, which is a roller that's on its own bearings out here, and was basically able to flip up out of the way when we were scoring into the amp. The note could kind of come out straight. And then when it was held against the wall by the trap, because you're climbing up on this like polycarb surface, that roller helped force the note down and into the trap because it was held up against the wall after it climbed. And so that little bit of play without having to actually like add an extra motor or have anything powered differently allowed us to amp a lot nicer, allowed us to trap this year because we had that moving piece there that could move around when we did it. Okay. The elevator itself, before we go on to climber, because these are both pretty similar, are basically a just a motor and chain. So here's our motor. This gearbox is called a max planetary, and we have it outputting into a max planetary 90 or a max 90. And this gives us a unique ability to be able to just drive a hex shaft directly. So it has this through bore hex shaft, so we can have a really long output without having to have like an extra gear or anything connecting it, or belt or pulley or anything. And so this is very convenient to package, and it makes it very, very simple. The max planetary also has it's a big advantage. You can change the gear ratio here. So if we wanted to have this have more gear reduction, we can add multiple stages, or we can change the stages. And so it allows a lot of flexibility in season to change how we want this to work without having to redesign much of anything. We could just do it on the robot directly without having to get back in CAD and make a new gearbox or anything. So this shaft connects all the way across the robot to a bearing on this side, and it has these two sprockets and these two runs of chain, and they are what actually do the lifting up and down of the elevator. So if the elevator is in its up position, the motor turns this way, and we have these blocks here that are mounted to the chain, and so they can start pulling down this whole mechanism, and we can very easily position control that so we know exactly where the elevator is. Whenever we tell it to go to a certain set point, we can know exactly where it's going, and it lifts up and down. The elevator itself rides on these bearing blocks. So we have ball bearings again. There's ball bearings pretty much anytime we have any sort of long distance motion or fast motion. We're going to use bearings to have that help be the sliders And so these are going to roll along the surface of this tube, both on the outside faces, and we have bearings on the inside here that roll along the inside face. And then we have another set that are stationary up at the top that are doing the same thing. And so that's kind of what you want to do in almost every elevator design. Some of just elevator basics is you pretty much want these two sets of bearings to get moving close together as it extends. So as it goes up, these bearings get closer together, and then as we go back down, they get really far apart. Um, and so that's pretty much the basics of how almost every FRC elevator works, is something along those lines. Sometimes you'll have all moving bearings and they have to like catch back onto here. That's kind of a unique situation. We do have to have something to hold the chain up at the top. So we have these idler sprockets up here. So these are just spinning on bushings. So this is a place where we couldn't use a ball bearing like we would want to. So this is just a bit of brass that has oil and lubricant kind of built into it. And since this mechanism doesn't spin all that fast, we're not too worried about it needing to be a ball bearing. It does probably lose, it's a little inefficient. It loses some energy to heat or friction, but that's okay in this regard. It doesn't actually hurt us that much. It's not moving that quickly, and it allows us to package it into this really small space that we needed it to be in, right? Because you can see the clearances here are pretty tight. These are almost touching, but we allow them not to because we have designed it well in CAD. So this is one reason why we have to CAD everything. You wouldn't want to try to like build this without knowing exactly how close it's going to be in real life. All right, so looking at our climber, these are actually somewhat connected systems. So the top sprocket of our elevator is spinning basically as an idler, so it doesn't spin at the same time as the shaft spins. It just spins on top of it however it needs to on the power shaft for our climber. So this hex shaft here is driven by some sprockets. So we have some sprockets here that work with the chain. And now we have our motor and gearbox that actually does the climbing. It's mounted here in the back. Again, it's this max planetary gearbox. We use it a lot if we're not 100% sure which ratio we need or if it's going to package nicely. This works out very well. It was into space that we didn't have anything else. So we didn't need to build a custom gearbox here. We could use one that we can just grab off the shelf and go. It has an output sprocket that's going to turn that shaft. And then it's going to turn these two chain runs, which are our main climber runs. This took quite a bit of iterating too. We originally had these carriages for our climber that would actually slide up and down these rails, kind of like how our elevator does. They'd have bearings that rolled on these tubes, but it wasn't quite giving us enough height, and so we ended up changing the way we did it, and we bolted these nut strips directly to the chain, so the chain has holes in it, and we were able to use number 440 bolts, some really tiny bolts, but several of them. So we had like 4 bolts going through into the chain there and bolted down. And then we had some metal plates on the outside here with a 3D printed little insert sandwich on the inside. And that let us directly mount the hooks to the chain without having to have any guide bars or anything here. So we wouldn't necessarily want to do this in every mechanism, but since the climb only had to happen once a match, we could tell if it was going to work. We could tell how it was loaded. And we did end up having to put quite a bit of chain tension on our actual climber posts to make sure it could actually hold the robot. So as these hooks go up, which I don't know if they do in CAD, I don't think they do. Oh, they do. One set of them does at least. There's like another set. They're able to, or is this just free? Oh no, those are just free. Those actually aren't mounted. Okay, I'm gonna undo that. They would just ride up and down the chains here. We'd be able to drive into the chain that's on the stage of the field. The chain would kind of get locked into this little loop here, and as we pull back down and are still driving backwards, we're able to grab the chain and it lifts the robot up. It works in combination with our amp trap, so that's the part that's going to roll and kind of slide against the wall as well. to be able to take us all the way up without the robot just like tipping over or anything. In addition, we did have to chain tension any chain runs that you have. The chain itself will actually stretch, even though it's made of steel. If you use it enough, it will start stretching a little bit. So you always want to be able to tension any chain mechanism you had, especially if they're highly loaded, like these ones are, where they're holding like the whole weight of the robot. And so we build in these little turnbuckles because this chain never loops all the way around. It's not like our intake or launcher belts or anything. They only ever run from this position up to that position. And so if we look on the robot, there's a little tensioner here that allows us to basically kind of bolt the two pieces of chain together and change their length a little bit, and we can make them tighter. And so we were able to do that nicely here, and on our elevator we do the same thing. And that allows it to make sure the chain's never going to like hop off the sprocket like you would have on like your bike. If your chain ever came off your bike, you know how annoying it is. We don't want that to happen in a match. So we use those chain tensioners to prevent that. We couldn't do that here. We had this chain run coming from this motor. And for basically the same, if you can think about how long this one is, this one ends up being shorter. And so you couldn't just have a chain tensioner in the same place that you do here, as it's eventually going to try to hit this sprocket and want to like go around it, but it couldn't. So it would stop our climb height. So we had to be able to tension this chain in a different way. And so we did that by just basically using the same or a very similar turnbuckle. I think we made one for this. And so this bolt here and this bolt here, one side has an opposite turn screw, so it's a left-handed screw. And so for that one, when you turn it counterclockwise, instead of getting looser, it actually gets tighter. And that lets us tighten this up and pull this whole plate down towards this bolt. And so because we could do that, we could tension this chain well, even though we couldn't put an inline chain tensioner in the chain itself. We could basically accomplish the same thing by moving this whole mounting plate and using this rail to kind of slide it down. So we never actually bolted into any of these center holes. We just had standoffs on the outside that we would use to like clamp the whole thing. And then you'd have this as our tensioner to pull it all the way down. The other parts of this robot, I'm going to go pretty quick because we're already at like the hour. This robot has 5 different limelights on it. The limelight is a smart camera, basically. It's able to do things for us and do some amount of computations on what it sees, and then send information back to the main controller of the robot. So we have one here on the left side, one on the right side, one on the front up here, and then we have 2 on the back. So this one on the back here and the other 3 that we showed are all doing the same thing. So these are used for April tag localization, which means they're able to see these like very simplified QR codes called April tags that are placed around the field. And then when the camera sees it, it's able to know its position in relation to like the center of the robot, and it knows where the tags are supposed to be on the field itself. And from that, it can calculate where it thinks the robot is based on where it's seeing those markers around the field. And so if you have 4 cameras on all sides of the field, no matter kind of which way your robot's looking, it's hopefully going to be able to see some of those tags and always be able to know where the robot is actually on the field. And with that information, you can do things like aim at the goal, turn the certain direction towards the amp to score into it. You can help in autonomous mode when it's driving around on itself. It can like relocate itself and then make its positioning a little bit better there too. So there's a lot you can do if you know your location on the field. The 5th camera here is pointing down, and so it's pointing down out in front of the robot's intake, and so it's used for actual note tracking. So it has a machine learning algorithm running on it, and so it's trained to detect that orange circle that is the game piece this year. And so it was used for any time that the pilot couldn't actually see the notes. There was a couple corners of the field where like if a note got stuck in the corner, there's nearly nothing you could do as a driver or pilot to be able to actually see it. And so in that case, the pilot could basically just point the robot the back of the robot in the general direction, hit a button, and the robot would automatically try to align and go get that note off the ground. So even if we couldn't visually see it by the human, the robot could go do it on its own. Other parts that were like climber parts that we didn't really talk about, we have the support bars. So a lot of the robot things are also making sure that the structure of the robot is going to be strong enough to do everything it needs. There's a decent amount of load when the robot actually goes and climbs. The whole robot's trying to sort of rotate backwards and push against this assembly. So we want to make sure that these rails down here are mounted well enough that they're not going to start bending when the robot's climbing or anything. We want to make sure we have enough mounting points and places to run wires, and just sort of support the whole robot wherever we can. I think that's pretty much everything about our 2024 robot. I don't think there's anything we missed. Yeah, the vast majority of the robot is done out of laser cut components, some routed components where we need metal, and then a lot of the pre-punch tube from either Rev or West Coast Products or Last Anvil, depending on whether we needed like thick wall things or not. Yeah, so that's pretty much how we were able to get everything we wanted the robot to do packaged into a relatively small space. You can see a lot of things are almost running into each other. There's a lot of little things that we have to make sure don't clip or hit or anything like that. So all of it gets done in CAD to make sure that we're not having any interferences. And we're still able to accomplish everything that we need to in this game. All right.